So now we are going to look at some algorithms. Let us look at an algorithm for finding the max-min value. Now that will work for n players. So we can use it often for 2 players, constant sum game, but the algorithm for max-min works for n players. It's also good, when you, for n players, regardless whether it's constant sum or not. It's also useful, for example, when we want to talk about the maximum safety level, we want to, security, we call it, that we just look at max-min in a general game without necessarily requiring constant sum or 2 players. So it's a general algorithm. So the algorithm works as follows. If the game is finite, just check all the options. And now if it's a mixed expansion, then solve the following LP. So you maximize this value. It's not necessarily that it exists actually, the value. It's not necessarily even a zero-sum game, but maximize V, the variable V, which is one variable, and also there is a vector variable, vector P. And P multiplied as a matrix, as a vector by matrix A from the left, has to be at least the vector of V. So you may say it's V times some horizontal vector of 1. So it means that every player, at worst, regardless what the other player does, the other players being here, the other players, because A can be not it's two-dimensional for 2 players, it can be n-dimensional. So regardless what the other n-1 players do, the utility of player I, whom we look at, of the player who we look at, will be always at least V star. And this minimum we want to maximize. So we maximize V star. And the only condition that is just left is to demand that P will be actually a mixin. And of course it's not negative and sum is 1. So that's all. And so the variables P and V. So that's one. The other algorithm we are going to show now is finding an Nash equilibrium of a constant sum to play game. Of course, you can always use the general algorithm, but here we can use something else too. So given a constant sum game with 2 players, we iteratively delete all the strictly dominated elements. As in any game, we can just delete them without changing the set of Nash equilibrium. Then check where the max min of U1 is equal to min max. Now, if the game already is given happens to be a mixed extension of a finite game, that means always holds. Because it's equivalent to the existence of a Nash equilibrium, which we know for a mixed extension of a finite game is always. Well, the mixed extension of a finite game is always the case. But in general, we have to check it. And if no, if it doesn't have a hold, return no Nash equilibrium. Otherwise, we look for yes. Otherwise, if this does hold, it means that there exists at least one Nash equilibrium, and those are exactly the max min of each player. So we look at them, we have an algorithm for that, and then we return simply the scalar product. So any max min of one of the players, any max min of other player is a Nash equilibrium, and these are exactly all those. So the Cartesian product of those sets of max min of both players is exactly the set of Nash equilibrium. As I said, they are exchangeable, so you can kind of match them in any way you want, and it will be an equilibrium. Or of course, you can also use a general algorithm. Find a Nash equilibrium.